So like Yusuf said, I was a postdoc during the West2 project, in charge of compiling, not creating, but compiling all the information to create the flat file that will be used in the West2 data project. Before I go on to the details of the database, I'd like to at least mention that this was a large group effort. There was no way that one person can do this, compiling the database, checking the information, creating the information. But I would like to specifically mention Bob Dara. He was a key player in all this. He spent as many hours as I have. Even before me coming to the project, he was probably the one creating the database in the West1 project, along with Brian Chu. For the outline of my presentation, I'll go into the characteristics of the updated database. I'll review again what the new spectra that we're using, that's being used in the West2 ground motion prediction equations. I'm going to overview the peer data processing procedure, and then finally end up with a description of the flat file, which is the public distribution of the information in the database. So again, just to reiterate, in the West1 project, there was a database released. It's a uniform processed ground motion consisting of free field stations. On this is a graphic of the magnitude distance distribution of those stations. There was a total of about 3,500 stations. In the West2, again, just to reiterate, we collected all significant worldwide crustal events up to November 2011. The last event was the Christchurch event in New Zealand. The red data points are the additional data that we added from worldwide events. Just to have a perspective on where those events were located, I have a graphic of where the hypocenter locations for the events in the West2 database. The blue dots are the events that were included originally in the West1 project. The red stars are the events that we added in the West2 project. And you can see that a lot of the data is being collected from events outside California. Not to reiterate too much, but there was a significant number of stations that are coming from 4 events from Japan events, with all moderate to large magnitude ranges. There are two significant events in New Zealand. Also in China, there was the large Wenchuan event, but also 64 aftershocks were collected in that data set. And then again, the L'Aquila, and then additional aftershocks in that event, and then 1 event in Iran. For the events in California that were collected, I just wanted to go over again. There was this magnitude 7.1 El Moyo Cucapá event, 7.2 El Moyo Cucapá event, and then the Parkfield and San Simeon events that occurred after the completion of the West1 project. In addition to collecting worldwide significant events, there was a major effort to include, again, small to moderate magnitude events, but specifically from only California. This is a plot of the hypocenter locations of the events that were included in that data set. Originally, we looked at about 300 plus events. The total number of events here is about 264, 260 events. The graphic shows 2 colors. So what we did was to increase or to get a better quality data on the event information, say the hypocenter location, the mechanism, the magnitude, we split the events up into 2 different regions. The blue zigzag line corresponds to the Gutenberg-Byerly line, which separates the Northern California seismic network, which is labeled events labeled in blue, and the Southern California seismic network, which is the events labeled in red. The reason for doing that is that most of the events in those two zones will have stations that recorded those events in those zones. So if the event happened that was red, there was going to be a less number of stations in the Northern California seismic network in that data set. So we didn't want to constrain the event information from networks outside that produced the recordings. So in the two different zones, we have hypocenter databases and then also fault mechanism catalogs that we reviewed, and we pulled information from those and were used with respect to those zones for those events. This is a plot, again, just to reiterate the number of stations that were included in this data set. This is a magnitude closest distance plot of the stations, and you can see that the magnitude range goes from about 5.5 to a magnitude 3. Magnitude 3. We have a large distribution of distances from close stations to far stations, out to about a maximum, I think, 1,000 kilometers. And just to overview the metadata that was driven, that we used to collect this data, we collected data from 4 data providers. So those data providers are the United States Geologic Survey, the Berkeley Digital Seismic Network, Caltech in Southern California, and the California Geologic Survey. The instruments that were collected were broadband seismometers and also strong motion accelerometers. And again, to reiterate, the collection of this data was motivating to have multiple events recorded at the same site. So a lot of aftershock sequences were collected in this small magnitude range. And also we wanted to have a review of the contrasting ground motions between the Central California and the Southern California regions. So when we combine those two data sets, the worldwide crustal events and this California small magnitude events, we have the full NGA West2 database. Just to overview some of the key changes between the NGA1 and NGA West2 project, we have a new rotated spectra, which is the ROT-DNN. There's 11 new damping ratios provided, and also period range was extended up to 20 seconds. For a quick discussion on ROT-DNN, just want to go overview how this is calculated. So what you do is you combine the two orthogonal ground motions to create a single ground motion along a certain azimuth, and that you create over different azimuth ranges. The non-redundant angles is 0 to 180 degrees in terms of rotation angles from the as recorded. You calculate the response spectra from that time series, and then you record the over all rotated angles. You sort them based on their magnitude, and then we record 3 fractiles. The minimum, which is the NN 0, the mean, which is the NN 50, and the maximum, which is the NN 100 spectral amplitude. And again, the reason we're doing this is motivated by the building code community is using the maximum component. But we also wanted to use a rotated ground motion. So the ROT-D50 ground motion is going to be used to develop the ground motion prediction equations. A comparison between the ROT-D50 and the GM ROT-I50, which was used in the NGA West 1 project, was presented in Dave Bohr's paper in 2010. So to switch gears, another significant component of the database are the time series. And so we want to review the time series processing routine that was developed and used by Pierre. So we continue to use that methodology. I have a graphic, which is a flowchart on the right. You're not meant to look and review that, but just to know that there are many steps. It's a very complicated routine. It was originally programmed in 4chan, and we ported that into R so that we can speed up the processing and process the small to moderate magnitude events in California. So with respect to that, about 19,000 recordings made it into that data set, but we reviewed about 40,000. So it was a major effort to review all of those independently and to make sure that we're using high quality records. And with respect to that, there was many people that contributed to the data processing, many hours, I think 5 or 6 different people that we had to bring along that were master's students, PhD students from Berkeley over the summer. But we finally got that done. Another important thing to note that there's a major difference between the NGA West 1 and NGA West 2 is during the filtering process, it was decided that we're going to process with an acausal filter. So anything that we could get the raw data for, it was processed with an acausal filter. The last note, and it's an important one, is that the acceleration, velocity, and displacement time series, they are all compatible. And in the NGA West 1, there was a discussion afterwards whether or not to use truncated records where during the filtering you add 0 pads, and then when you truncate that and then integrate, there will be an inconsistency between the acceleration, velocity, and displacement. In the routine for the baseline correction after the filtering, we remove the 0 pads, and the AVD plots or the AVD time series are all compatible. So you can go from one to the other without too much error. Another thing to note, that's even though we say that we try to expand to a larger period range, what that means is that we had to reprocess the entire NGA1 time series set again. So this is a graphic of the periods that we're using in the NGA West 2 project as compared to the NGA West 1. The red triangles are the periods that we've added in the NGA West 2 project. And the effect of reprocessing all of those time series, there was a significant effort put into reviewing the filter corners and the filter cutoffs that were selected before, and we were trying to increase the usable period range for the time series that were in the NGA West 1 project. This is a graphic where the x-axis is the lowest usable period range for the record, and then the number of records for that period. The comparison is done based on the original 3,500 records in the NGA West 1 project. As you can see, the NGA West 1 usable number of records for that period range is shown in the solid curve. The NGA West 2 project is shown in the dashed curve. What you can take away from this is at a longer period, say around 10 seconds, the number of records that could be used in the ground motion prediction equation has more than doubled. So that even though that they were using the same time series, this was a significant effort to reanalyze whether or not you can push that filter corner out. And I think it has a significant contribution. After the time series processing was done, all of the spectra and all of the metadata for those records and the events had to be combined. And what we do is we combine the most important information and we put it into an Excel sheet, and we call that the flat file. The flat file was generated from 3 different databases. And so I'll go and overview those databases here. The first database is the source database. It records the source information, the magnitude, the hypocenter location, the depth to the top of rupture, and which is shown here on this graphic to the right, to the left, sorry, to your right. And then the rake, the dip, and the strike, the length and the width of the fault plane. But also, the source database has much more than that. There were many alternative hypocenter locations that were considered. But what we fed into the flat file was the preferred information and only a subset of the key information. The second database was the source database. That consists of all the source to site distances in addition to the directivity parameters for each station. The graphic to the right shows the hypocenter distance, the closest distance to the rupture, the epicenter distance, and the joiner bore distance. Just as an example, again, we only pulled key information from that path database, and that was included into the NGA West 2 flat file. The last database we call the site database, where each record, each station that's included in the ground motion database was given a specific identification number, and then we collected site information for that, those specific stations. The most important information And I don't want to go over too much detail of the site database because John Stewart is going to be doing that after this. But the most important information that we pull from the site database is the VS30 for each station. And also, there was a large effort to update that information. So if there was a recording, if there was a station that had an inferred VS30 value based on, say, geology, and that station has a VS profile, we updated that VS30 to have a measured value. Just using that as an example, we did this for many of the other different metadata that's included in the site database. So this was a major effort. In addition to that, there was a large effort to reconcile a lot of differences in the station information. So location, the name, the identification of the station, so that we didn't have duplicate recordings in the database in an error. So that was not easy. It took a coordinated effort with Bob Dara and many of the data providers, and additionally with John Stewart and his students at UCLA. So when we combine all of those key information from those three databases with the spectra that was said earlier, the as recorded, three components, the wrote DNN and the GM wrote I50, we create different flat files based on those different combinations of metadata and spectra. There was a large effort to QA the information that went into that. A lot of the meetings we were discussed based on many different groups. The site amplification working group, the directivity working group. We all discussed and used the database, used the information in the flat file, found errors, and then corrected those. That was not an easy task, and it took many meetings and many different times of using it. As it got updated, I think the information improved significantly. In addition to improving the quality of the information, and just adding the information for additional stations that we put into the database, we wanted to include additional metadata that was not provided in the NGA West 1 project. This is just a quick list of that. Just to be brief, we included a new event classification for the events, a new district distance metrics that was not provided in the NGA West 1 project, new directivity parameters, new late trigger flags, and then we also, in an improvement of the database, we removed co-located stations so that if a station or a location had two recordings, two different types of recordings, we only included the best recording or the most reliable recording at that location. Just to overview some of those data points, I'd like to just briefly mention what this new event classification scheme is. In the NGA West 1 project, each ground motion prediction equation developer had to evaluate if the event was a main shock or aftershock, and that was done independently between the developers. In the NGA West 2, we wanted to have a consistent framework to identify these events. I'm not going to go into how that was done. That will be presented later by Katie Waddell. But I do want to say that we are introducing a new classification, 1 and 2, where Class 2, I hate to say it, but it's what we call before as an aftershock, is an event that's in close proximity in time and space to a past rupture surface. In terms of new distant metrics, the NGA West 1 did not include RX. So a graphic to the right just illustrates what RX is. It's the distance perpendicular to the top of fault trace. And you have a plan view and a side view of that RX value. And it can take a positive or negative value depending on where you are relative to the fault trace, the top of rupture. In the NGA West 2, we are recording two new distance metrics, generalized U and T. T is the same as RX, and those were detailed in Spudich and Chow 2008. The graphic to the right just illustrates what those are. The generalized U is the distance from the top left corner of the fault plane that's projected to the surface, and the generalized T is just the perpendicular distance from the, the surface projection of the top of rupture. In an effort to increase the quality of the time series or the information for that's included into the database, there was a review of those time series done by Bob Dara. We removed co-located stations, like I said before, but also we reviewed the time series in terms of what recording quality we can assess. So each instrument was looked at, and we wanted to know if it recorded the P and the S wave, or if it just missed the P, or if it missed the S wave. And so we created a new flag that will be included in the flat file that will say whether or not the S or the P wave was missed. That will be a significant contribution for triggered instruments, where they will most likely be missing the P wave because they may be triggered on the P or the S. But the modern data, the modern instruments are digital, and they have a large pre-event time, and so the flags will not correspond to these stations. And so these corresponds to many of the stations that were included in the NGA West 1 project. So as a summary, the database is I would say, the largest uniformly processed database in the dataset in the world. It has a magnitude range of 3 to 7.9, closest distance range of 0.7 to 1,500 kilometers, a VS30 range of 90 to 2,100 meters per second. And it was a significant effort to pull all this information. The database can be used by structural, geotechnical engineers, as well as ground motion hazard analysts and financial loss modelers. The database, like I said before, will be used to update the ground motion prediction equations for the west coast of the United States. And it will be available April 2013. Thank you very much.
Great. Thank you very much, Tim. Why don't you wait? The database, as I mentioned, really was major effort that we put together the various pieces, and many eyes looked at it from different angles, and we found typos, errors here and there. Questions for Tim before we go to the questions from the internet audience?
You need the mic for the recording.
Okay.
Yeah. Thank you. Okay. All right.
Well, I have a question.
Yes, go ahead.
Okay, I saw that you have a parameter now that distinguishes aftershocks from main shocks. What about foreshocks?
You're going to hear that. Katie is going to support that.
Okay.
You're going to show that. She's going to show that in after lunch,
Okay,
immediately
thank
after. It's very interesting. It's different than classical way that we have been working. You will see detailed presentation. Hamid.
I wonder if the definition of aftershock is similar to what we have in USERV3 project, or it's different.
I think, I'm not sure, but I think they're different. At least for the time being, but we have to converge.
And then just a comment, we talked about a late trigger flag. I wonder if it makes sense to have a flag for spikes. In some records, there are some spikes. I mean, just a comment.
We will consider that, yes. Thank you.
More questions for Tim?
I'm not understanding why the sudden emphasis on magnitude 3s. I looked at the definition, and the displacement at 100 kilometers is 5 times 10 to the minus 4 millimeters, about 1,000th of the thickness of a fingernail. And it has the energy equivalent of 15 gallons of gasoline. What problem are we trying to solve by, and could you elaborate on why we're doing this?
You want to say?
As I mentioned, not emphasis on that. This is just expansion of database. You're correct. For engineering point of view, you have to deal with much more important challenges, especially if you're close to the fault. The issue really was that previously we were over-predicting the ground motion at a smaller magnitude, which, again, you may not care for engineering design for life safety. However, when you go to the other parts of the world that they have only a small magnitude data and they compare to our models, then there's a mismatch. Then they had to adjust it, and then they made serious mistakes in that. That was one motivation. The other motivation was that we needed repeated recorded motion at the same site to find out the specific characteristics of the site that we can take care of that in terms of standard deviation. If we want repeated recorded motion at the same site, unfortunately or fortunately, we are not going to have lots of magnitude 6, 7, 8 at the same site. We don't have so many earthquakes. We have to go to a small magnitude that we get more often, more recorded motions at the same site. So there are lots of reasons. And then another side reason of that, which I didn't mention it, we have other projects for Central Eastern U.S., is low seismic region. And in Central Eastern U.S., we have only or mostly small magnitude data. And if we want to understand the characteristics of the west versus east, how much information we can transfer from west to east and so on, we have to compare apple to apple. We cannot compare magnitude 7 to magnitude 3 in the east. We have to compare magnitude 3 and magnitude 3. That's another motivation. But overall, you're correct. If you want to design a building, a bridge, and so on, and life safety is your only concern, that's not a big deal. Again, it's not a major emphasis. It's just expansion of the database.
So I notice you have a maximum VS30 now of 2100. I'm not quite sure what the maximum was before, but one thing I'd like to know is, is there a substantial increase in the number of hard rock sites that for which we actually know the VS30 as opposed to an inferred VS30?
I think John Stewart might have a graphic for this, but I think the proportion of rock to soil sites is about the same in the NJ1 and NJ2. So we didn't really increase the percentage of those stations.
All right, thank you.
More questions?
Given that there was an M9 earthquake in Japan, why was it too difficult to include the ground motions from that event? Because it seems to be one of the extreme ones.
Yeah, so that was an easy question. This is a database of shallow crustal earthquakes in active tectonic regions, so we're not collecting subduction zone events.
And then, Zifa, as you know well, we have other parallel project unrelated to this project on subduction. So we are collecting same amount of, in terms of details, same information, VS30 values, all the records and processing the records for subduction earthquake. That's NGS subduction that we started a few months ago. It will continue for a few years. But we are going to compile really one of the largest databases in the world about subduction earthquakes. But this is mainly shallow crustal California type and Western U.S. and Middle East and so on. Jerry.
In the flowchart you showed on an early slide, at the bottom there was a trigger for recalculating with a new filter that you described as if the displacement time series were acceptable. How did you measure the acceptability of the displacement?
Yeah, that is a very difficult question to answer. It's a very subjective thing.
That's the same then
Exactly.
as the way we did it years ago, that if the displacement looked noisy, you changed the filter.
That's exactly right. So if you see like there's some long period wave that you would see that would come from noise or some other than signal, you just pull the filter corner back. that would remove that.
More questions? No? Okay, Christine received 2-3 emails from the audience connected on internet, and Christine, please read.
Okay, I'm the voice of the people online. Vladimir Grazer has 2 questions. The first one is why the database flat file will only be available on April 15th, not earlier?
Well, the reason, as I mentioned, is because we are not ready really for full public use of these things. We are still working on that. This is the first public workshop that we have. We want to share with you what we have. Still, as I think literally as of 1 a.m. just this morning, I received an email, I think, from Brian Chu. He's still digging into this, and he was asking questions from Tim and others. Oh, by the way, that specific record is such and such. So we are still working on that. For the same reason that the GMPEs will be released publicly in that time frame, because we are still working on that. We find errors, typos every hour basically, and then once we are really ready, because we know once we release it, we cannot take it back. People all over the world will start using these things for analysis and design of dams, bridges, and so on. We don't want to rush into that. We are working on that literally day and night to make it robust. We are going to release it as soon as we are comfortable. Really.
The next question is, again, from Vladimir. How did you combine broadband and strong motion? Broadbands are velocity.
So if we had, excuse me, if we had a station location that had the broadband seismometer and a strong motion instrument, we selected the strong motion instrument for those cases. For stations that only had the broadband seismometer, we had to use that data.
Okay, Nico Luco had a good question here. Are you recording this, and is it going to be online, and when?
Yeah, this session is being recorded. As I mentioned, I was semi-joking. We may post it on YouTube. Depends, really. But definitely is recorded, and very likely we can post it as a minimum at peer website that you can watch it later, and possibly even on YouTube. Everything is public.
Okay, another question from Anil Yunachi. I hope I'm not butchering the name. Dr. Ancheta, will there be a browsing module software release for viewing, querying the database in Companion with the flat file in Excel format?
I think the flat file will be in XLS, but the time series or the spectra, I think, will have to be queried from the peer digital ground motion library.
So it's going to be this an application similar to what was done for West2, right? West1.
Exactly.
Okay.
Yeah, that website is extremely popular, and one of our colleagues was saying we immediately, if their electricity enrichment fieldization goes off, before we hear back from our colleagues in Richmond, we receive emails from Germany that, oh, the website is not working. And so it's very popular. After the database is really final, then the interface, user interface will be updated. We are going to add more features. Because, for example, right now you can download only 5% response spectra. Now you will be able to download all the spectra that we have, time series and other things, and the amount of the information that you download now is very limited. You cannot download many files at the same time. So we are going to improve it after the database is ready. More questions? Oh, okay.
Hi, thanks. Is significant duration addressed at all in the flat file?
So, yes, I did fail to mention we're going to be recording at least one duration metric. So the Arius intensity between 5% Arius intensity and various others. That's I think the only duration we're considering.
How about Arius intensity itself?
So for the entire time series, you can take it from that file, yes.
Is that was
that was going to be my question too, about
Oh, in the
It will be a separate flat file, yes.
it will be one of the things that you can download from the peer website. Flat file basically is the information that the GMPE developers use to develop their models. If they use, for example, hypothetically, ARIAS intensity, we'll include. If they didn't use, it's important information. But if they didn't use it, we are going to include that into the website that you can do it. That's next, after April. There was one last question somewhere? No? Yes. Last question.
Does the database cross-reference with liquefaction or significant liquefaction effects?
Maybe I misunderstand. Are you referring to recordings on liquefied sites or metadata with respect to liquefaction?
If you find a record, will you have knowledge of whether there was significant liquefaction, not necessarily at the site, but with that earthquake? I mean, there you have 19,000 records, but if you wanted to find earthquakes with liquefaction with a database, pull that out for you?
No, we did not record whether or not that site liquefied at the moment, but we can look into that.
Great. Thank you very much, Tim. Appreciate that. Really, Tim was a key person in the database along many others.